So thank you all for coming. I'm Matthew Heydeman. I'm a graduate student at Caltech. And I'm going to be talking about a version of the AdS CFT correspondence, a discretization of the correspondence based on some ideas from number theory, in particular the P-Adic numbers. So this talk is based on work with Matilda and some of my collaborators at Caltech, and then later also with Matilda Marcoli, sorry, and then later also with Stephen Gubser and his students. So there's quite a lot to read on this slide, but got to move on. Just as an overview, first I'm going to introduce the idea of AdS CFT, which I think everyone should be familiar with a little bit already, and maybe some of the motivation, why we'd like to discretize the AdS CFT correspondence, and maybe how we might do that. Since I think many people might not necessarily be familiar with the P-Adic numbers, I'm going to do an informal review of the P-Adics. And then I'm going to show that some lattice models of scalars in a discrete bulk geometry are naturally holographically dual to some conformal field theories defined over algebraic curves over the P-Adic numbers. I'll talk a little bit about these field theories in detail, discuss a potential bulk action for gravitational dynamics in the bulk, and then just some future work stuff. So I'd like to say that I'm hoping this talk will be a fun talk. I won't be particularly formal or do a lot of calculations on the board, but I'll have a lot of pictures, so that should be fun. So AdS CFT, this very successful program that relates quantum gravity or string theory in anti-de Sitter space to some conformal field theories that live at the AdS boundary. Best understood examples are these brane configurations, like this famous one of Maldacena. But even without a precise bulk boundary pair, it's possible to understand some model-independent aspects of the theory, particularly in low dimensions, like AdS3 CFT2, and there's been work on geometry from entanglement, Riemann surfaces, SYK, and things of that sort. But despite the successes, it's a strong, weak duality. Many challenges remain, and sometimes it's very hard, for instance, to understand things happening in the bulk. So one of the ways to address some of these issues, particularly the bulk and the quantum information, is to introduce tensor networks in the bulk. So the idea here, maybe I've sampled this picture from a paper of Preskel, is to, rather than talk about continuous gravity and a conformal field theory, perhaps tessellate the hyperbolic plane with some tiles, introduce tensors, and then these tensors are supposed to represent isometries, a flow of quantum information. And in particular, if I delete some region of the boundary, I'm supposed to be able to reconstruct it. I'm supposed to be able to, it's equivalent to deleting some region in the bulk. The bulk is in some sense redundant, and these models are cooked up to reproduce the Ryu-Takeyanagi formulas. But there's some problems with the discrete models. When you do this kind of tessellation, when you introduce these tensors, you often break the conformal symmetries. So AdS CFT was supposed to be a theory about conformal field theory and gravity, and doing something like this totally breaks the symmetries. It doesn't really have field theory dynamics, and maybe the full boundary theory is unclear. So the question I'm posing, that of course I'm going to suggest one answer to, is there a version of the AdS CFT correspondence that's more similar to the continuum models? So can we define real field theories and preserve the conformal symmetries and the isometries of the bulk? And the answer will come from doing something very algebraic. So what are some hints that this question might have an answer? For instance, hints from mathematics. So in low dimensions, the conformal field theory, I'm going to work in Euclidean signature for the rest of the talk. And in low dimensions, the conformal field theory, the space-time of it, is defined, for instance, on the projective line over the complex numbers, or the projective line over the real numbers, depending on which dimension you're working with. These are algebraic curves over some number field. Now, it's possible to construct algebraic curves over other number fields. This has been known for forever. There's an entire branch of mathematics. And it's interesting to ask, well, can we use some other fields, make a projective line over some other fields, and see if there's a holographic dual? In a sense, I'll explain shortly. One way to arrive at some new fields are, for instance, metrically completing something like the rationals. So the rationals, you could think of them as the series of rational numbers, and to metrically complete them means to define some procedure to fill in the holes, so to speak. And normally one would complete the rationals with respect to the real norm, but we can complete the rationals with respect to another norm, which is the P-Adic norm. So I'm going to review a little bit about the P-Adic norm now. So the real norm I'll denote with this little infinity down here. But the P-Adic norm will be defined as follows. So we take any number in the rationals, and we can uniquely write it as this factorization. So we pick any prime number, and most of the time in my illustrations I'll use 2 or 3, those primes, but any prime is fine. And we pull out the largest power of the prime that we can, raised to some positive or negative integer exponent, and then there's some rational number where a and b are coprime. So this is sort of a unique factorization of any rational. Once we've done that, we define the P-Adic norm to be p to the minus v. So v was the exponent of the prime. The norm is just p to the minus v. Now this is a pretty interesting norm. And it has power law behavior, and it also only takes on discrete values. So it looks very different than the real norm. But this is a nice hint that we might have something to do with the CFT. It's a power law scaling, but it's also discrete. It has some of the ingredients I talked about before. Maybe some examples. So the P-Adic norm of 0 is 0. The P-Adic norm of the prime itself is p to the minus 1. And in general, if I have some series, I pull out the biggest power of the prime that divides the number, and then the P-Adic norm is just p to the minus that number. Now this norm is ultrametric. It obeys a stronger version of the triangle inequality. And in particular, the P-Adic norm of a sum of numbers is always less than or equal to the max of the individual norms. So maybe some statement you could say is that all triangles are isosceles in the P-Adics. Now there's this century-old theorem of Ostrowski that says that every non-trivial norm on the rationals is equivalent to either the P-Adic norm or the real norm. So these are really two cases that are worth studying. And there aren't other stranger ones, I suppose. So now I'm going to define a P-Adic number to be some power series. So we take the p to the nu. So this is sort of the magnitude part. And then we have an infinite series where these coefficients here run in 0 to p minus 1. Maybe I could call this the residue field. Now this is a Cauchy sequence. And it actually converges in the P-Adic norm because the P-Adic norm is p to the minus this power. So this looks like this is a divergent series, but it's actually convergent in the P-Adic norm. And the set of these convergent Cauchy sequences defines the field of the P-Adic numbers, which I'm going to denote QP. Now, much of what we do, we can do for finite extensions of QP, such as QP to the n or some general ramified or unramified extension. But let's move on and just focus on the simple case. So if you're like me, you like to have a picture of what's going on. And so I'm essentially, by drawing this tree structure here, I'm graphically representing this infinite series I told you about before, where each branch is labeled by an element of the residue field. So here, QP, this would be a 0 and this would be a 1, for instance. And the P-Adic numbers are going to be down at the boundary of this infinite tree. And each one is specified by a unique set of values as I move out to the boundary. And the P-Adic norm also has some nice interpretation in terms of geodesic distances on this tree. So I haven't defined this tree. I just said it was a graphical tool. And I haven't said anything about holography yet. But if you just look at this picture, it's a little bit suggestive of what's to come. So my goal is to convince you through some explicit calculation that if we put a lattice model on this infinite tree, it's going to be dual to some field theory that lives out here at the boundary in a way that's very analogous to ordinary AdS CFT. So there's some hints from physics. The physics has also employed P-Adic numbers in other contexts. The main one is a P-Adic string theory, where, for instance, the bosonic string boundary we replace, instead of with the P1 of R, we replace with P1 of QP. And there's a nice formula due to Brecker, Freud, Olson, and Witten that is essentially an integral form of the Veneziano amplitude, the 4 tachyon amplitude of the open string. Simply by replacing real norms with P-Adic norms, we get this P-Adic string amplitude. It's not clear why it's useful, but it's interesting to think about. And now there are other hints that these P-Adic field theories might make sense. So there's, for instance, hierarchical models. These early founders of the renormalization group studied discrete models where, for instance, I take pairs of spins and add an interaction between them, and pairs of pairs with a weaker interaction, and so on. These are sort of bi-local StatMech models where RG in a discrete sense works exactly. I like to think that these guys, if they knew more about primes and AdS CFT, they might have discovered this idea, as in some cases their models are exactly what I'm going to talk about. So there are some nice similarities between R and QP. For instance, P1 of QP has all the conformal transformations that we'd like, and in particular, they're fractional linear transformations. So if X is a P-Adic number, X goes to this Mobius transformation is actually a conformal transformation of P1 of QP. It's exactly the same as how it would work over the complex numbers or the reals. There's an integration measure, and indeed we can define functions over the P-Adic. So for instance, a real or complex valued function the space-time is the P-Adic numbers, and these are so-called Bruhat-Schwarz functions. And there's a notion of a plane wave and a Fourier transform. So we can do some ordinary field theory technology on this space, even though we've given it a very unusual topology compared to the reals. There are also these magical formulas from number theory known as Adelic formulas. This first one, it looks innocent enough, but it's in a way it's equivalent to saying that every rational number permits some unique prime factorization. So I invite you to recall the definition of the P-Adic norm and the real norm. And when I take this product over all of the P-Adic norms and the real norm, I actually get 1. There are more interesting examples of Adelic formulas. For instance, Tate's famous thesis where he proves the functional relation for the zeta function, the functional equation for the zeta function involves some P-Adic Adelic products for these so-called local zeta functions. And that Veneziano amplitude I told you about before also obeys this, which tells you that the real Veneziano amplitude can in principle be computed from the infinite product of the prime ones. So now I need to talk about the bulk spacetime now. The bulk spacetime, as I mentioned before, alluded to, was this infinite tree. And in Euclidean space, for instance, the bulk hyperbolic 3-plane can be written as this coset space PGLTC over the maximal compact subgroup, and it has the boundary P1 of C. Similarly for H2. And so the isometries of this coset space are equivalent to the boundary conformal transformations. This is the first hint of the correspondence, that the symmetries of these two spaces agree. So our idea is to just replace R or C by the relevant formulas for the P-Adics. Oh, just as a picture, this is a picture of the boundary plane P1 of C, and then the bulk hyperbolic space in Euclidean is sort of attached to the boundary. And you can imagine dilatations, for instance, will scale this circle and scale this geodesic surface. There are also black hole solutions that can be constructed purely algebraically by a process called Schottky uniformization. So we pick some discrete subgroup of the conformal group, quotient both the bulk and the boundary by this discrete group, and so we get some identification under scaling, for instance. This would be a genus 0 curve. So the boundary spacetime under this identification becomes a torus, and the bulk becomes this filled-in torus. So I would call this the Euclidean BTZ black hole. So we can do all this algebraic stuff over the P-Adics as well. We constructed the bulk and boundary spaces as algebraic curves and cosets, and we can do the same here. So we can take the conformal group, mod its maximal compact subgroup, and this space is actually discrete. It's the Bruhat-Titz tree, known as the Bruhat-Titz tree, and it's an infinite tree of uniform valence that we saw earlier. So that's the algebraic setting. Now I need to, show you a picture of it again. Hopefully this makes it look very much like the ordinary case I just described. There's another representation that makes it look more like the Poincare disk instead of the Poincare half plane. And there's some infinite geodesic here that corresponds to a unique point on the boundary. And there's black hole solutions. These boundary curves are sometimes known as Mumford curves. But I won't talk too much about these higher genus curves for now. We'll stick in the flat case. So I want to now do the simplest thing I possibly can. It's almost naive, which is to take some real valued scalar fields defined on vertices of the tree and write down a lattice model, a statistical mechanics model, nearest neighbors in fact. So I'll sum over pairs of nearest neighbors, taking the difference of the scalar on those neighbors, squaring it, and maybe adding some potential energy. So this is just a lattice model of statistical mechanics on this tree. Now we can linearize this action and find the equation of motion, because I'd like to do some semi-classical field theory. So for instance, there might be in this potential might contain a mass term, and we have that the lattice Laplacian is equal to the mass term acting on phi. So there's some Klein-Gordon equation. And so now the bulk-to-bulk propagator, or the Green's function for propagation between two bulk points, it's not hard to show that this equation is solved by p to the minus delta d. So this d would be the integer distance between two bulk points. And this thing solves the equation of motion, where delta is related to the mass through this formula, which has a zeta function expression. This delta is going to end up being the conformal dimension of an operator that couples to this theory in this field in the boundary theory. So this formula simply states the relationship between the conformal dimension and the mass of the scalar that we put on the tree. Now, in addition to the bulk-to-bulk propagator, we also need a bulk-to-boundary propagator. It's labeled by a boundary point. And so the distance to a boundary point is formally infinite. So we have to do some regularization. But once we've done that, this is essentially now the P-Adic analog of a bulk-to-boundary propagator in the usual space, in the usual AdS space. And there's also a BF bound. It's known that in AdS, the masses of things can be slightly negative, just not too negative. So we find that by minimizing the previous equation, we get a BF type bound as well. Okay. Now, following Witten, we're going to uniquely construct a bulk function by superposition of boundary functions. So I pick some boundary conditions on this scalar, and then I integrate over the boundary space times the bulk to boundary propagator. This for a given boundary condition constructs a unique function in the bulk that satisfies the equations of motion. And then we make Witten's holographic ansatz. So essentially, we do a saddle point evaluation of the bulk partition function corresponding to the boundary value we choose. And that is supposed to be dual. This is a semi-classical computation that's supposed to give us the generating function for correlators for this operator in the CFT. So I said that we need the saddle point evaluation. We can do this calculation omitting some details, and we get a non-local boundary action. This is sometimes known as a generalized free field action. We get a non-local boundary action. And from this action, or directly from functional differentiation, some more work will show us that the two-point function of these operators is exactly the kind of thing you would expect for a two-point function in a conformal field theory of some scaling dimension delta, except now I've replaced the real norm with the P-Adic norm. So if you're familiar with all what CFT should look like, this is one of the first things you see in a CFT, except we just have the P-Adic norm instead of the real norm. So this is a very stark agreement between these real and non-Archimedean or P-Adic spaces. Higher point functions like the 3- and 4-point functions were computed by Gubser, and there's, I'd say, detailed agreement with ordinary AdS CFT. What I mean by that is you take the answers you would expect from the real case and replace them with P-Adic norms, and you get up to some normalizations, the same stuff. So this is good evidence that we found some kind of duality between putting matter on a lattice model, integrating out the lattice, and arriving at some quantum conformal field theory on the boundary of that. So I better move a little bit quicker here. I think I've spent maybe a bit too much time talking about background material, and the main derivation. So there has been some systematic study of purely boundary theories now. So maybe we have some conformal primaries that transform under fractional linear transformations according to this weight, and 2-point functions work the same way. 3- and 4-point functions are constrained strongly by the ultrametricity property I talked about. And there's a nice interpretation in terms of these geodesic Witten diagrams in the bulk. So the constraints on boundary correlation functions are sort of dual to the fact that the bulk is in some sense very trivial. And just to be sure we're not crazy, we could set up a free scalar, a free boson, and just do the usual path integral quantization of this theory. This is just a purely boundary calculation. boundary calculation is occurring, and I won't discuss it in detail. But as you might expect for a free boson with conformal dimension 0, at the end we get a logarithmic divergence of the correlator, which is the kind of thing that happens for a boson over C. There's a log divergence for a conformal dimension 0 object in the CFT. There's also some other nice things we can do. For instance, non-renormalization theorems. If the radial direction in AdS CFT is supposed to be some RG direction, that sort of triviality or lattice nature of the bulk actually corresponds to the fact that when we do Feynman diagram calculations, just purely boundary calculations involving scattering of particles, or for instance, renormalization of the propagator, we find that we never get renormalization. And you can use this to compute things like anomalous dimensions in O of n models, and again, you find great comparisons with the real cases. So these are in some sense discretized trivial field theories that, well, not completely trivial, but they're more trivial than their real counterparts, and you can compute lots of things exactly. We also talked about these so-called SYK models. So these models are the inclusion of boundary fermions. And in order to understand this, the boundary fermions, you need some notion of sign characters, quadratic characters. And in particular, rather than studying the SYK model, we study these Klebanov-Tarnopolsky-Witten models, which are fermions that transform in a weird flavor group. These models are supposed to be dual to black holes, and they have allegedly universal IR behavior. So I've given the free term in momentum space and the interaction term. It's a 4 Fermi interaction where we've contracted indices with some flavor group. And detailed computation using a bunch of P-Adic integral technology that I alluded to its existence but didn't actually explain in detail shows that we can actually solve this theory at large n with a Feynman diagram calculation in the IR. This amounts to solving a Schwinger-Dyson equation. So we have a free propagator and a renormalized propagator. We can actually, and these are convolutions, we can actually compute this using P-Adic integrals. And we get universal conformal type behavior in the IR, where this constant here is related to some Gelfand-Graev gamma functions, which I don't have time to explain. But we find that independent of this spectral parameter in the ultraviolet, so there's a large family of ultraviolet models, they seem to flow to a universal Kitaev type IR type models. Universal IR behavior. So maybe this is indicative of some black hole type features as discussed by Kitaev. I think I'm nearly out of time, so maybe I should briefly mention that we tried to do some theory of the gravitational dynamics using a paper by Yao and his collaborators. They were able to define some notion of Ricci curvature on graphs without the Riemann tensor, because we don't have a holonomy. This led to some expression for the curvature in terms of the edge lengths, AX, Y. And from this curvature expression, we found that on shell, this tree had constant negative curvature, and that the fluctuations are a massless mode. So I think it's a little too early to call this a graviton or some notion of bulk gravity, but maybe it's some kind of dilaton gravity or something like that. And we compared the holographic duals of this linearized mode to field theory as well. So I'll briefly state in conclusion, I think there's a lot of this story that we still don't understand, but we have some good evidence that at least if I put scalars in a fixed background on this infinite tree geometry and do the usual AdS CFT machinery, we can define define conformal field theories on the boundary. But some things that we'd like to do is really find a precise pair of bulk boundary theories, 2 consistent theories that are exactly dual to each other. Or if not that, at least an interpretation of the ON or SYK models, and perhaps a connection to the P-Adic string. And it would also be nice to use these adelic formulas a little bit more to reconstruct things about ordinary AdS CFT from the P-Adics. So one can imagine over the P-Adics, it's very easy to compute all these things. I told you about non-renormalization and a lot of calculations we can do exactly. It would be nice to use these adelic formulas to reconstruct real smooth AdS CFT from that. Or maybe from a mathematical point of view, maybe we could use the AdS CFT picture to understand new things in number theory about L functions, for instance. Also maybe holographic entanglement entropy, bulk geodesics, and perhaps the connection with the holographic codes that I briefly mentioned at the beginning. and also higher dimensional cases. So there are higher dimensional versions of this tree that are buildings like cell complexes attached to each other in this infinite space, and maybe there are holographic duals for these kinds of spaces as well. So quite a bit left to do still, but I think we at least understand something about the mapping in this case that I've described. So I think I've run my time.